I don't even know where they're from.
Sorry?
Someplace called Harvard.
And someone in Germany, according to my list.
Why didn't she catch that? I didn't even spell his name right. His first name and last name are both spelled wrong. He sent me an email 2 days ago complaining. He's like, please get this changed. I'm like, it's a little late for that.
Okay, so welcome back for the second installment of the L functions and arithmetic geometry session. First of all, according to AMS rules, I'm supposed to remind everybody to turn their cell phones off or at least put them on silent. And then I will, without further ado, William Stein is going to start us off with the P-adic BSD for GL2-type Abelian varieties.
All right, thanks. So it's a nice manageable sized audience compared to the last talk that I just was at. By the way, if you want to get the slides for the talk I'm giving now or for what just happened an hour ago with Barry Mazur, they're at wstein.org/talks, and they're just listed or linked to at the top. So what I'll talk about today is the P-adic Birch and Swinnerton-Dyer conjecture for abelian varieties of GL2 type, which are up to isogeny and decomposition as products of simples, exactly the same thing as abelian varieties attached to modular forms for gamma 1 of n and weight 2. And I'll focus entirely on modular forms for gamma 0 of n rather than gamma 1 of n, except for a remark at the end. And this whole talk represents joint work with Jennifer Balakrishnan right there and Stefan Miller, who's somewhere in Germany, as you'll find in the notes. Also, there's a paper that's on the archive and linked to from my website, which gives kind of every detail related to this. And there was also a talk by Jennifer, I think yesterday, which pretty much had the same title and so on, but will be somewhat different than my talk, or was somewhat different. Okay, so first, I'll talk a little bit about the classical Birch and Swinnerton-Dyer conjecture for elliptic curves defined over Q and point out some subtleties. So as hopefully everyone knows, there's an L function attached to an elliptic curve and a conjecture that Birch and Swinnerton-Dyer here made about that L function, namely that the order of vanishing of the L function equals the rank of the curve, and there is a formula which is that the leading coefficient of the L series of the curve about s equal to 1, so in this talk we're normalizing not about s equal to 1/2, but about s equal to 1, is equal to the regulator of the curve times the real period omega. There's some normalization that goes into defining the real period omega, so that you can say the. There's the order of the Shafravich-Tate group, whose definition is given right here. Whoops. So here's what SHA is. It's the kernel of a map from a global H1 to a direct sum of a bunch of local H1s. And then you have times the Tamagawa numbers C sub p, which are the orders of the rational points on certain component groups, and divided by the square of the order of the torsion subgroup. And the situation regarding theorems, summarized in a way sort of as quickly as possible, there are other kind of pages and pages, of course, of theorems, but the main theorems can be summarized as follows. First, if the order of vanishing of the L function is less than or equal to 1, then you know the first part of the conjecture, namely that the order of vanishing equals the rank. And the second part, which I'll call F for formula, in principle and in fact in practice, you can verify it in particular cases. There are algorithms in computers, in Sage, for example, that will take as input a curve and verify that the full conjecture holds on the nose. In principle, this could seem like a dauntingly difficult question where you might have to compute, Selmer groups for a very large number of primes p, which would be impossible in practice. But it turns out that in many cases, because Shafrovich Tate groups just tend to be rather small, and the bounds that you get out of various theorems are quite tight, you can verify this in practice. And just to give a sense of the state of the art, Robert Miller, Michael Stoll, myself, and many other people have verified this conjecture for curves up to conductor 5,000 that have that satisfy the hypothesis that the rank is at most 1. There are curves of much smaller conductor than 5,000 that have rank 2, and of course then the hypothesis isn't satisfied. The next kind of branch here is that if the order of vanishing is at most 3, then you don't actually know for sure that the conjecture is true a priori, but if you take a particular curve and decide to work a little bit with the computer, in practice you'll always verify that the rank equals the order of vanishing. So basically there's an algorithm which takes as input a curve of analytic rank at most 3 and will output either yes, the first part of the BSD conjecture is true, or no, it isn't. And you can run it and it's efficient, reasonably efficient. Unfortunately, if you look at the second part, for curves that do not fall into the first setting here, that is for curves with analytic rank 2 or 3, there's not a single example where the formula has been verified. In fact, it's really quite bad. We don't even know that if you take this formula and put all the transcendental factors on one side and all the integers on the other side, that in fact the quotient involving the transcendental factors is actually an algebraic number. For all we know, it's a transcendental number rather than a rational number. So the situation is very bad as far as the exact formula goes for curves of rank 2 or 3.
Is it also the case that in no such case we know that Shaw is finite?
That's correct. I will give the state of the art regarding data towards finiteness of Shaw for the second case that I'm describing there later in the talk. And that really motivates the whole project that I'm talking about. When the order of vanishing is at least 4, then we don't know anything at all. So there's not a single curve for which the order of vanishing has been shown to equal the rank. And moreover, as it follows from what I just said, in principle, you can't even verify this. There's no algorithm that might take a long time to run that we know about, which would output either, yes, the curve has analytic rank 4, and no. So there's, for example, the smallest conductor of a curve over Q with algebraic rank 4 is 234,446, 234,446. And we don't know that the order of vanishing of the L function is 4. It's definitely greater than or equal to 2, but it might be 2. If you compute the second derivative and evaluate it at 1, you'll get 0.00000000, but for all we know, 100,000 zeros later, you'll suddenly get a 7. So we just don't know.
Has the fourth derivative been shown to compute to be non-zero?
Yes. Yeah, that's easy to do. So it's either 2 or 4. Okay, next, BSD for GL2-type Abelian varieties, which, there's a theorem due to Serre, Ribbit, and a whole bunch of modern people such as Kari, Winton, Berger, Wiles, etc., which says that these are exactly the modular abelian varieties. So if you take an abelian variety over Q that's simple and whose endomorphism ring is as big as possible, so it's endomorphisms that are defined over Q, when you tensor it with Q, you just get a number field of degree equal to the dimension of the abelian variety, then that abelian variety will be isogenous to an abelian variety attached to a modular form. The special case of dimension 1, the endomorphism ring hypothesis is automatically satisfied, and the statement is that every elliptic curve over Q is modular. But that generalizes and is fully proved now. In that setting, there's a new form floating around, and you have an abelian variety which you can think of as attached to the new form. I'm specializing to the case of gamma 0 of n, but of course there are new forms that are for the bigger group gamma 1 of n, and pretty much everything I'm going to say makes sense in that context as well. However, it's just a little simpler to talk about gamma 0 of n. So associated to the new form f, you have an abelian variety, which I'll call a sub f, following Shimura's notation, and it's a quotient of the Jacobian of x naught of n, the Jacobian j0 of n of x naught of n. It's an abelian variety whose dimension equals the degree of the field generated by the Fourier coefficients of the modular form f. It has endomorphisms by the ring generated by the Fourier coefficient, so it has an enormous endomorphism ring defined over Q, and so on. And it has an L series, which is the product of the L series attached to all the Galois conjugates of the form F. And here's the conjecture. So I'll zoom out a little to show you some of the theorems. So the conjecture looks exactly the same as what I just stated for elliptic curves, the only difference being that instead of the square of the order of the torsion subgroup, it's the order of the torsion subgroup times the order of the torsion subgroup of the dual. I'm not sure whether anyone's given an explicit example of one of these A sub f's for which these two numbers are not equal, but I'm sure it happens. But I actually haven't seen one. Okay, and theorems. The theorems they're kind of like one step back just because abelian varieties are more difficult to deal with. In principle, the theorem should be exactly the same for A sub f's as for elliptic curves, but in practice, they're certainly not. So if the order of vanishing of the L function is less than or equal to 1, that is the L function of the modular form, not of the abelian variety, the order of vanishing of the L function of the abelian variety will presumably be, conjecturally at least, will be the dimension of the abelian variety times the order of vanishing of the form. That's what should happen and does for small order of vanishing. But if the order of vanishing of the L function of the modular form is at most 1, then the rank equals the order of vanishing. And this follows from work of Colley-Vaughan and Grossagier from the 1980s involving Hegner points. And the formula, in principle, there should be algorithms which will take as input a specific form F and output whether or not the full Birch-Swinnerton-Dyer conjecture is true for the abelian variety A sub F, as long as it satisfies this hypothesis. To the best of my knowledge, except for a couple of cases of A sub F's that happen to be Jacobians of curves, for which you can use very different methods than what you use for elliptic, or than what you, I mean, there are various special cases of specific computations that would not generalize to all A sub F's for which this has been done, but it's a very small list. So there are a couple of cases where F has been verified, the formula has been verified, but it's, for example, all elliptic curves for which it's been verified. And there are a couple of dimension 2 A sub F's where it's been checked. But there are a large number of abelian varieties A sub F for which it should certainly be possible to come up with a way of checking this sort of thing, but it hasn't been done yet. It's difficult because you're presented with A sub F by giving a modular form rather than equations for an abelian variety. And so you have to find equations for the abelian variety. And if the abelian variety isn't, say, the Jacobian of a curve, then it's just a quotient of a Jacobian of a curve, then it can be difficult to do explicit calculations with it. Nonetheless, it's an area of active research, and it's getting poked at. But it's not in nearly as good of a situation as it is with elliptic curves. And then the other situation, if the order of vanishing is at most 3, then in principle, you should be able to decide whether the order of vanishing equals the rank. But in practice, well, just writing down equations for the abelian variety is very difficult. Then doing a descent and finding points, if they should be there, gets very tricky in practice. Okay, next, P-adic BSD for elliptic curves. So, the statement is very similar to classical BSD, except the L function is replaced by a P-adic L function. This is a power series. Well, you can view it as a power series in QP double brackets T. It interpolates special values L of E chi 1 over omega E chi. And the tricky part in defining it is figuring out what these, how to make these quotients rational or algebraic integers in some systematic way, or not integers, but numbers in some systematic way, and sufficiently canonical way. And then you can interpolate special values, et cetera, et cetera. And I'll give, when I talk about abelian varieties in just a second, I'll give a formula which specializes to give this P-adic L series. And the conjecture looks almost exactly like the classical BSD conjecture, except now it's an equality of two P-adic numbers, and the various quantities, some of them are changed. So for example, the complex regulator, the usual regulator, which is a real number, is replaced by a P-adic regulator, which we can now compute very, very efficiently, even if P is around 1 million, and you want like 20 P-adic digits of the regulator, you can do that very, very quickly, due to work of David Harvey, Mazer, Tate, and other people. The Shafariach-Tate group is exactly the same one as you are used to, the same Tamagawa numbers, the same torsion. There's a number epsilon P which is related to unit root of x squared minus apx plus p, and there's a log factor as well. So there's a formula and an order of vanishing statement. This is the statement in the case when p is a prime of good ordinary reduction greater than 2. You can also make a conjecture when p equals 2. You can make a conjecture for super singular primes, which Rob Polak, for example, has studied extensively, and also for both split and non-split multiplicative. Additive is much more subtle. And there are theorems. So one theorem, which is much better in a sense than what you have for elliptic curves over Q, is that the rank is less than or equal to the order of vanishing. So if you have an elliptic curve of rank 4, like the one I mentioned earlier, you know for a fact that the p-adic L series really does vanish to order at least 4. There's one really weird thing, though. The regulator of an elliptic curve, the classical real number regulator, you learn when you're learning the basics of elliptic curves that it's non-zero. P-adic regulators, on the other hand, we know very little about whether or not the p-adic regulator is really non-zero. Conjecturally, it's always non-zero, but the theorems about it being non-zero are rather annoyingly limited. So you can compute in particular cases quickly and see that it's non-zero. That's what always happens instantly. But we don't know that it's non-zero, so this number a priori could be 0 right here. And many theorems have as a hypothesis that the regulator is non-zero, especially a big theorem of Peter Schneider. So if the regulator is non-zero and some other technical hypotheses are satisfied, then due to work of Peter Schneider, using Iwasawa theory, Kato, and so on, you have a really strong theorem towards the p-adic analog of BSD. And a weak consequence of it is that the conjectural order of Shaw is an upper bound on the actual order of Shaw at p under certain hypotheses. So if you want to take, for example, an elliptic curve of rank 2 and verify that Shaw is as close to finite as you can hope to get on a computer, that is, show that the p part of Shaw is finite for many primes p, you can try to verify the hypotheses right here and then compute the conjectural order of Shaw. But there's a conjecture for each prime p. So you have to compute what the conjectural order of Shaw according to the formula is for each prime p. Okay, so here's an example of such a result. Just make it a little bigger. So if you take the elliptic curve 389a of rank 2 and consider good ordinary primes up to almost 50,000, I ran out of steam at 48,859. And I also ran out of steam trying to deal with 16,231. Then you find that for all of those primes, the p part of Shaw is trivial. And you get this by simply computing the conjectural order of Shaw and finding it's 1 for each of these. And this shows an example of how you do that sort of calculation. And this is another theorem. So if you take curves up to conductor 30,000, I did a similar calculation for all the primes up to 1,000. And again, I find that Shaw is as conjectured by BSD. In all those cases, Shaw is supposed to be trivial, except maybe at 2. Okay, moving on to abelian varieties. The main issue is how do you define the p-adic L series? And there's a direction in which you can go that is very frustrating, which is that you say, oh, the p-adic L series of your abelian variety, it's the product of the p-adic L series attached to each of the modular forms. So your abelian variety is attached to a new form f. F has Galois conjugates. So you focus on a particular new form f, and you say, oh, the p-adic L series of A sub f is the product of these other ones. And so all I need to do is figure out how to define L sub p of f sigma. So for each new form, I need to define the p-adic L series. And so for that, you think, oh, I need to find a sort of notion of canonical periods. And it gets very frustrating because you can't find a good notion of canonical periods for a specific new form. And so I think we spent months dealing with this issue and maybe doing various contrived things. But at the end of the day, what you really care about is the product of all of these L functions for all the conjugates of f. And there is a canonical product of all the periods. Namely, you take the volume of the abelian variety A sub f, integrating using the neuron differential, which is just the A sub f that you have globally in the BSD conjecture. So all you do is you just make sure that the product of all these non-canonical periods. Just choose them however you want according to some recipe of Shimura, which guarantees that there are some reasonable periods with good rationality properties. Just choose them so that when you multiply them all together, you get the sort of the standard Archimedean omega a sub f, and that works. And then, so you just don't care that each of the individual L functions are not canonically defined. There's a choice for each one individually. You just make it so that when you multiply them all together, it works. And then with that, here's how you define the p-adic L series. It's just construction using modular symbols. It's exactly like what you do for elliptic curves over Q. And here's the conjecture you make, which is exactly like the conjecture for elliptic curves over Q. And here is numerical evidence. So we took 16, there they are. We took these 16 curves, which were from the first paper I was involved in, which was, we took a whole bunch of modular genus 2 curves back in like 1997 or something, and computed all the BSD invariants and solved for the order of Shaw. And this was an extremely involved calculation that really involved a bunch of different people. But at the end of the day, you have some data, and some of those were a sub f's. So in this project, we took those, we computed all of the quantities except the order of Shaw appearing in the p-adic analog that we made of the BSD conjecture, and then solved for the conjectural order of Shaw and got 1. And so that was good evidence for the conjecture. And just to give you a sense of how some of the data looks, so here are some generators for these curves. Particularly, there's a curve of conductor or of level 67 for various primes up to 100. These are what the p-adic regulators look like. These are what the special values of the L function look like, and the other quantities are pretty easy since they're already in the table of the paper from 15 years ago. Put it all together, and you get that our conjecture appears to be reasonable, which is also nice because it looks exactly like the one that you have for elliptic curves over Q. And just the very, very last remark to make is that these are really involved. The calculation of the p-adic regulators is perhaps much harder than you might imagine, since it's so easy nowadays for elliptic curves over Q. Though 10 years ago, it was a pain in the ass for elliptic curves over Q. But it's now really easy for elliptic curves over Q. It's now a pain in the ass for abelian varieties a sub f, but it's possible for a couple of them due to work of Jennifer and Kieran and Stefan and so on, which involves making Coleman integration explicit and doing stuff with intersection theory and so on. So it's actually quite sophisticated, the techniques that go into computing these p-adic regulators. Okay, that is what I wanted to talk about. Let me know if you have any questions. So I'll just flash that slide. Yes?
So, point 1, what's the difficulty here?
At 16,231?
Yeah, why was it,
So the I did a really highly optimized, as much as possible, I think, implementation of using classical modular symbols to compute the p-adic L series. That algorithm works wonderfully if you want the p-adic L series to low precision. But in this particular case, it's absolutely essential to get it to like precision p to the 5th, and because otherwise you can't verify the conjecture. And using overconvergent modular symbols, this should be doable. But it seems that nobody's done it. It's definitely doable using like Rob Polak's algorithm and Stevens. Yeah. So Polak-Stevens will do this. But I keep asking people to try, and they've done other things, but not this particular thing. And the same thing, so this was only checked for good ordinary primes. You could also do something at super singular primes, and there is an implementation of an algorithm, but it's, even for the first super singular prime, it's ridiculously slow, like 97, I think. So you need to come up with a much, much better implementation or algorithm. So fundamentally, a different algorithm will help. Okay, any other questions? Thanks.